Okay, let me give another reason why causality may be an illusion. This is called quantum entanglement and Bell's inequality. Now, quantum entanglement is well publicized in the popular science literature. I don't know if it's well understood, but I'm going to try to go through a step-by-step example to show in practice what it means. Now, here we go. All right. Now, we know that particles undergo radioactive decay, and another property of particles is that they have a attached property called spin. I'm not going to say too much about spin, but suffice it to say that all particles, all elementary particles, have spin. Okay. Now, when a spin 0 particle decays into two daughter particles, and suppose that these two particles decay in opposite directions, as they must because of conservation of momentum. Suppose we measure the spin of each of these daughter particles. Now, I should say that spin is measured along a direction. Okay, so suppose we measure the spin of daughter 1 particle along this direction, and we measure the spin of daughter 2 particle along the same direction. Now, the spin can end up being positive. I'll say this direction is positive. The spin can end up being positive or negative along this axis. Similarly, the spin over here can end up being positive or negative. Now, one fundamental property of spin is that spin is conserved. If I measure spin to be positive for this daughter particle, then the spin for this daughter particle must be negative. Absolutely necessary that the spin over here must be negative because the two spins must add up to 0. Okay, so there are only two possibilities, either spin positive here, spin negative here, or spin negative here, spin positive here. That is, of course, assuming that the daughter particles don't have 0 spin themselves. But the two spins of the daughter particles must add up to 0. So let me represent those two possibilities. Either this daughter has spin up and this one has spin down, or daughter 1 has spin down and daughter 2 has spin up. And that's true regardless of the measurement axis. I chose this particular axis, but I could have chosen it in a different direction. As long as the two measurement axes are parallel, I will get the same phenomenon that the spin over here must be the negative of the spin over here. Okay, so I got that? Now, it seems like this decision of equal and opposite spins should be made at the time of the decay. Just as when the particle decays, the two daughter particles go off at equal and opposite momentum, so we would expect the two daughters to go off at equal and opposite spins, regardless of what they encounter in the future. All right, now, we're going to see that that supposition gets us into trouble, and we'll see that in the next slide. Okay, so let's run with this situation a little bit. I'm going to set up an experiment where I prepare several spin 0 particles, and I prepare them all the same way. So we have spin 0 particles, and they're going to decay into two daughters, and I'm going to measure the spins, but I'm going to arrange the detectors differently. So I can run this experiment many thousands of times, prepare many thousands of spin 0 particles, and measure the daughter spins. And this is how I'm going to do it. So here are the two daughters, and I'm going at first arrange my two spin detection axes along these brown axes. So notice they're not parallel, they're skew. So it's possible to measure an upspin along this axis and an upspin along this axis. It's possible, maybe not very probable, but it is possible. Now, keep in back of your mind that when we have particle decay, if you measure the particles along the same axis, the spins are going to be anti-parallel. So keep in mind that although we're not measuring along this cyan direction, if we did measure along the cyan direction, we'd have upspin here would correspond to downspin here would correspond to upspin here. All right, so I'm going to run many thousands of experiments where I have my detection axes along these skew directions. I'm going to change the detection axes, and I'm going to keep this axis the same as in the first set of experiments, and I'm going to change this axis to be along the cyan direction. Okay. And then I'm going to run several thousand there, and then I'll change my axes again. I'm going to let this detection axis for daughter 1 now be along the cyan axis, and this detection axis for daughter 2 to be along the original direction here. All right, so I want you to notice something. As I said, every detection corresponds to either this pink or red case or this green case. So even though in this first experiment here, I'm measuring along skew axes, if these two daughter particles have already determined their states, they're determined in such a way that if daughter 1 is up here, it's down here, and if daughter 1 is down here, it's up here. So let's look at all the UU particles that match with the green case. Okay? The UU particles that match in the green with the green case would also receive this detection if the detectors were set up this way. Why? Because we're saying that we have the green case, so these two spins are anti-parallel. So that means that daughter 2, if measured along this axis, would measure positive. And we're only looking at particles that fit the UU case. So we'd have this detection along the daughter 1 axis. Right. So just to recap, all of the particles in the UU case that correspond also to the green situation would also receive a positive detection for the UG case. Okay. On the other hand, if we had particles in that get UU here, and they have the red case in the background, then that would give a positive detection for the UR case. Okay, and why is that? Again, because if we have red detection, then this would be red here, so we'd get here, and we're only looking at particles in the UU case, so from this detection, we'd have to have a detection along this direction. Okay, so in other words, all of the UU detections are covered either by this case or by this case. And this description is predicated on the idea that when the daughter particles fly off, in the back of their mind, even though the detection is not along the cyan axis, they still have equal and opposite spins along the cyan axis, even though that's not actually measured. Okay, so now we're getting close to the punchline. And let's think about this. We've talked about 3 possible setups for the detectors. And if the detectors are set up as the brown axes here, we talked about the UU case, where we have up in this direction, up in this direction. And we could run the same number of detections with the detectors aligned like this. And we could count the number of detections where we have up along this axis and up along this axis. We call this the UG case. And we could run the same number of detections with the detectors aligned this way and count the number of detections where we have up along this axis and up along this axis. And we talked about in the UU case that even though we're not measuring along the cyan axis, if the daughter particles have decided their state once the decay occurs, then in the back of their mind, we can say, they must either be red-red or green-green. Now, the ones that are red-red, when the setup is as over here, we'd get a positive UR case detection. And when the setup is green, green, we get a positive detection over here. So in other words, the UU case is covered by the UG case and the UR case. So if we ran this experiment, say we did 1,000 particle decays with the detectors like this, and 1,000 particle decays with the detectors like this, and 1,000 particle decays with the detectors like this, we would expect that the number of detections here plus the number of detections here should be at least as big as the number of detections here. Why? Because of this picture. Here I'm talking about in terms of number of detections. You can also think about this in terms of probability. The probability of this case should be less than or equal to the sum of the probabilities of this case plus this case. Now, is this in fact what's observed? And the answer is no, it's not what's observed. It turns out that there's a very simple formula for these probabilities that is derived from quantum mechanics. If I have two detectors like this, let's get this together. Suppose I have this is the detector for daughter 1, and this is the detector for daughter 2. And suppose there's an angle between them. I'm going to call this angle theta, which is what they usually use in geometry class or in physics to denote an angle. The probability of getting an up detection on this direction for daughter 1 and an up detection in this direction for daughter 2 is going to be equal to sine squared of theta over 2. Okay. Now notice here what I'm showing is the, well, this could be this corresponds to the UR case. Right? So that means that the probability of UR is sine squared over 2. Sine squared theta over 2. Now if I do the other two cases, if I look at the UG case, that's very similar to the UR case. Here I have this detector for, which one was this for? I think that's for daughter 2, it's straight up and down. And for daughter 1, the detector is in this direction. I have the same angle here. So in fact, I have the same probability. The probability of, and let's see, I think this was UG, is equal to sine squared over 2, theta over 2. Now what about the case for UU? Let's look back and see. For UU, we also have two detectors, the brown direction here and the brown direction here. But this time the angle between them is twice the angle that we had in the UG case and the UR case. So if we go up back here and we look at the UU case, we have one detector in this direction, one detector in this direction. The angle between them is now 2 theta, and we get the probability of UU is equal to sine squared of theta. Okay. Now we have this supposition. We're thinking that the probability of UR plus the probability of UG should be bigger than or equal to, so there's a question mark here, should be bigger than or equal to the probability of UU. And does this work out? So the question is sine squared theta over 2 plus sine squared theta over 2 bigger than or equal to sine squared of theta? So that's what we need to verify. And if our picture is correct, our understanding of the situation is correct, then this should hold. Now, you can take out your old trigonometry book and find double angle formulas and work this out, and you'll find out that this is not true. It's not true. It doesn't work out. Okay. Sine squared theta over 2 plus sine squared theta over 2 is actually less than sine squared theta. Okay, so Houston, we have a problem. It's not possible that a set is bigger than the union of two sets that contain it. It's not possible that the probability of an event that's included within two events has a larger probability. Okay, so let's summarize where we are. Particles cannot be consistently tagged following the decay. In other words, when the two data particles come out, we can't say they know already what they will record when they reach the detector. They can't be tagged as UU, UG, or UR. There's something funny that happens when they reach the detector. The detection results can't possibly be caused solely by the particle's history, independent of the detectors. The detectors somehow add some kind of secret sauce, because if you try to characterize them without considering the detectors, then you end up with a ridiculous result. Now, if somehow the particle does change its mind when it reaches the detector, then the detectors must communicate with each other instantaneously. Since when the two detectors are parallel, a positive spin on one detector always corresponds to a negative spin on the other. So you can think of this scenario where two daughter spins are coming off, two daughter particles are coming off, and one reaches the detector on the left and says, okay, I see this detector, and my spin is going to be a certain way, but I better check with my other daughter over there and make sure that my spin is opposite to hers. This is kind of a strange scenario, and there are many ways to, well, I don't know if there are many ways, but there are different ways to accommodate this difficulty. The usual way to accommodate this difficulty is to say quantum mechanics is mysterious, we don't understand what's going on, just got to accept it. But I would like to point out that if you jettison the idea of causality, the idea that the particle goes off and the subsequent history of the particle is determined by its past, if you jettison that requirement, then there's no problem at all. The problem only came because we said that as soon as the particles come off from the decayed particle, they must have a deterministic specification of what happens to them afterwards. Okay, so causality could possibly be the source of the problem.